Hi everyone. My name is Sun Meng. I'm a postdoc at Sierra, Northwestern University. Today I'm going to talk about how tides change the orbit of binaries and the new open source code to model stellar tides. Just want to clarify, during my talk, I do not for this stellar tides, we do not deal with mass transfer or mass accretion, just two isolated stars, they don't have mass interaction. And this work is in collaboration with Rich Townsend from UW-Madison, Phil Ayres from University of Virginia, Nevin Weinberg from University of Texas at Arlington, also Guo Zhao from University of Cambridge. So I would like to start with some basic idea of how tides change the orbit and the previous tidal theory. So let's focus on the cartoon here. We use a big circle to represent the primary star in the binary system, and there's a companion star rotate counterclockwise on this slide. And and the traditional theory of tides, we think friction causes tidal bulges that lag behind the companion rotation. To simplify this issue, we can use 2 point masses to represent the 2 tidal bulges, and due to the gravitational force, there's a 2 force generated due to the tidal bulge point to different directions. And the combination of the force can produce a torque that can slow down the motion of the secondary star and also shrink the orbit. This is under the assumption that if the primary star is a slow rotator, if that is a fast rotator instead of orbital shrinking, system will expand just due to tides, just like Earth, Moon, and Jupiter Io system. And we can use this equation here to express the rate of change in semi-major axis. And some interesting term I would like to mention is that the first one is the stellar radius, the rate of change in semi-major axis is very sensitive to the primary star's radius and also the semi-major axis itself. Another interesting term here is the last one. So the capital omega here is the star spin rate, and the lowercase n is the orbital frequency. So for fast rotating star, when omega is greater than n, so that makes this term negative and makes the whole equation positive. So that means system will expand. So traditional traditional theory of tides treat the lag time as a free parameter and also calibrated by observation, and sometimes treat this lag time as a constant during the evolution. We don't do that. We just trying to calculate this term actually case by case. I'll talk more in detail in the following talk. Okay, the next one is the physics of the tidal flow. Astroseismology, usually that refers to the self-excited mode inside the star, and it can be analogous to simple harmonic oscillators. But the tidally forced oscillation can be, it is just forced oscillation. So what we do here, we add a extra forcing term in the fluid momentum equation and solve them solve it numerically. The solution for the wave function is the combination of the short wavelength solution and the long wavelength solution. The long wavelength solution is the equilibrium tide, which is the instantaneous response due to the time varying gravitational potential. A good example is the tidal bulges racing on Earth caused by the moon. The short wavelength solution is actually the dynamical tide. It is the resonant excitation of the internal stellar internal gravity wave, and is a wave-like response. And here I have a plot that's showing the 2 different kind of solutions. On the top panel, I give an example. I give the stellar structure of this example star. So inside the star is dominated by the radiative zone, and outside that there's a convective envelope. And we can see in the stellar convective zone, the solution is dominated by the non-oscillatory equilibrium tide, and in the stellar radiative zone, the solution is pretty oscillatory, and this is dominated by the excitation of the dynamical tide. So after talking about like mode excitation due to a companion, the next I would like to talk about like mode damping mechanism. First one is the turbulent viscosity in the stellar convective zone, like in damping the equilibrium tide. So let's focus here. Like there's two layers of fluid inside the star. The lower layer move towards left, and upper layer move towards right. If we have a test particle in the lower layer, so when it's moving upward, because it initially carries the momentum towards left, so it will like slow down the radiative motion between the two layers. And during this process, there will be a shear force generated. And this shear force is proportional to the molecular viscosity. And we just use the mean free path of the test particle times the thermal velocity to calculate the molecular viscosity. And other than like test particles or molecular in the stellar, inside the star, there are actually like large eddies in the stellar convective zone. And it's also like, because of those eddies, it's also like slow down the radiative motion between the hot and cold layers. To calculate the turbulent viscosity, we use the size of the eddies times the eddy velocity. And because the size of the eddies is much greater than the mean free path of a like molecular, so actually in the stellar convective zone, the turbulent viscosity is pretty important, like in damping tides. And we also need like the turbulent viscosity in calculate the energy dissipation rate like caused by tides. Another very important damping mechanism is the radiative damping. That is very important in massive stars. The propagation like of the dynamical tide, like because it's wave-like, so it's like during the propagation, it creates some compressed and decompressed region inside the star, and the compressed region are hot and the decompressed regions are cold. Heat flow will like moving from the hot region to cold region. If the heat diffusion like distance is greater than the wavelength of the wave, we can say like this wave is strongly damped due to the radiative damping. On the plot 2 plus, I'm just want to show you guys like how the diffusion, like radiative diffusion, like plays a role in damping the like wave-like response. The top one is actually an example of weakly damping like wave. So we can see the adiabatic solution is is equivalent to the non-adiabatic solution. So that's an example of like weakly damped or like non-damped like a radiative damping mode. The bottom plot like gives an example of strongly damped wave. So the response like of the non-adiabatic response is close to the equilibrium tide solution. So yeah, so this is how the radiative damping like cancels the wave-like response. In the second part, I would like to talk about a little bit about a new open source code to model stellar tides. Like we call this code as Gyrotype. I talk about like in the very first few slides, the traditional like approach to study stellar tides like usually deal with like some parameterized equations, and that method like usually like overestimate the orbital shrinking rate, but also sometimes like underestimate the orbital like circularization rate. Gyrotype doesn't suffer these limitations, because like we just solve the wave, like the forced wave equation numerically, and we do not have approximation, even we don't apply like WKB approximation. Hopefully like Gyrotype can give us like a new idea to help us better to analyze the observations in binaries or even like exoplanet systems. The motivation of our work is the tides in massive stars. By analyzing Kepler data, Thomson et al. 2012, they discovered a new class of stars called heartbeat stars or heartbeat binary systems. The name just comes from its light curve. So it's just like electrocardiography. And this is the example like light curve for the heartbeat systems. And we can see there's a central peak like here. This is caused by the equilibrium tide when the companion star pass near the periastron of the system. And we also see like there's some high frequency oscillatory feature are excited. This is the excitation of the dynamical tide. And usually the heartbeat system is in a very eccentric system. Kavli mission discovered about like 173 systems that has this heartbeat feature. And it varies, like most of them are like A to F type stars. That means like they are sort of like close to like solar masses and up to 2.5 solar mass. This is just an observational bias because Kepler do not observe like too much like massive stars, but some other like space and ground-based observations, they found like this heartbeat phenomenon also like exists in O and B type stars, which means the heartbeat system like can exist in a binary system containing a star as massive as like 30 solar masses. Here I would like to highlight some beautiful results from Gyrotype. This is like modeling like the radial displacement and the flux perturbation as a function of forcing frequency. For the KOI 54 system, this system is a face-on Kepler system, which containing two A-type stars, and they are kind of equivalent in mass. They're all like 2.3 solar masses. The orbital period of this system is 42 days, and it's also very eccentric, if I remember that right. It's about 0.8 in eccentricity. Okay, so the solution, like the result, like for the surface response, like near the surface of the star, like if we force the star in a like very slow speed, or like the forcing frequency is kind of small, which correspond to this part of the plot. Like this region is just dominated by the equilibrium tide. And when the ratio between the forcing frequency and the orbital frequency is like near 20 to like 30, this region is dominated by the excitation of the dynamical tide, but they are kind of like radiative diffusion damping plays an important role here. So like the flux variation is not that big. And let's move to this region. If we force the primary star in a very fast rate, that's the excitation of the dynamical tide, and the response here is weakly damped by is non-damped by the radiative damping. Gyrotypes can also calculate the change in orbital elements such as semi-major axis and eccentricity. Here I'm just showing like the plot for the time scale of the orbital shrinking time scale and also the circularization time scale as a function of orbital period. This example system has a 5 solar mass main primary star, and there's a 1.4 solar mass neutron star orbiting around like this 5 solar mass main sequence star. So generally, like the time scale is shorter when the orbital period is small, and the time scale is longer for longer orbital period. This is just because like the tidal strength has a strong dependence like on the orbital separation. And we also see there's some like big spikes like on this plot. This is the excitation of the dynamical tide, which can also like bring the time scale to a much smaller number. All right, so like at the very last of the slide, I would like to, it's more like a discussion because like something is not super, we are not super confirmed. So here I'm just trying to like, there are two methods like in calculating the stellar response. The two methods are overlap integral approach and the direct forcing method. The first one, overlap integral approach, like is that we think the star response is represented as a linear superposition of the star's adiabatic free oscillation modes. And we also thought like that kind of mode is orthogonal. And the amplitude or the weight like of those mode is calculated by evaluating the overlap integrals between the tidal potential and the eigenmode itself. The advantage like for using this method is that it's sort of like, because there are a lot of like open source code in calculating the eigenmode for any like given stellar profile, including the regular gyre. But it's sort of like computational expensive, or we need to really be careful about like calculating the coefficient like between the like before the mode and stack them together properly. The direct forcing method is just like solving the forced wave oscillation directly. And here, like on this movie, I'm showing the comparison like between the two methods, overlap integral method in blue and the inhomogeneous or the direct forcing method in dotted orange line. And we can see like there's a disagreement near the surface of the star, where the where the non-adiabatic effect is kind of important. So there's a disagreement like near the star surface in between these two methods. And another disagreement like between these two methods is the when we force like, so the different frame here is that like we're trying to force the star near a eigenmode, but not exactly at that place, just like trying to force the star near that eigenmode and to see like how the star responds. Out of resonance, like these two methods also just get kind of like disagree. So at here, like we are kind of argue that like the overlap integral approach, because it's assume a constant like damping rate. So it may, I mean, get a not correct, like it may got a like wrong result, like when like running like stellar or calculating stellar response in like superficial layers, which means like where the non-adiabatic effect is kind of important. So yeah, we need to be careful like when calculate the tidal response in using the overlap integral approach. Okay, I would like just to stop here and take questions. Thank you.
Hi, thanks for the nice talk. I wanted to ask in the plot where you were showing the circularization time as a function of period. Mm-hmm. How narrow are those more or less very low circularization times?
Oh, like let's see, it's like 10 to, it's varying from like 10 to 4th to 10 to 8th year.
But I mean in period, if I zoom into one of those places where the circularization time drops to essentially a year even, how narrow in period is that? Because if a star tries to circularize, it will move in period, and then it would move out of that more or less resonant place.
Or do you mean like the parameter range, like we run like dealing with the orbital period, like we are running like, okay, this for this example system is like 5 solar mass main sequence star and the neutron star in the 2-day orbital period. So like somewhere here. Mm-hmm. And the time scale can like for the orbital shrinking is about like 10 to 4th to 10 to 8th like year. So that means like maybe like up to 0.1 gigayear. So is that the
okay, maybe I can ask you directly afterwards.
Oh, yeah, sure.
Okay, someone else.
I have a question. Sorry. Did you?
No, please go ahead. I was just pointing at
are you able to compare your results with the actual amplitudes observed?
Oh, you mean like light curve-ish like things? Yeah, this is also one of the functionality we are just trying to, now it's still in developing. Like we just like by having the surface amplitude, we're trying to convert that into a real light curve, like in different band even. Yeah, like this definitely like will be a future function, like new functionality in gyre. Yeah, thanks.
Lars Bilston, nice talk, Meng.
Thanks.
You showed a plot early on that had a non-adiabatic mode that was quite deep, and you were getting to the equilibrium response. for a non-adiabatic calculation where the G mode was very deep within the star. And I was curious how what was the setup for that one? Because the radiative time is so long, even though it's a high order mode. I was curious how what was the setup for that? Was it a really wide orbit?
Oh, for this one.
Yeah.
Don't quite remember. I still like running a massive star here, maybe a 5 solar mass, like zero age means like a slow pulsating B star. We usually use that as an example. And for the top one, we like scan near the number 8, like the G8, like eigenmode. For this one, I think if I remember that right, it's like G40, like So like, G like, or like any mode like smaller than, or like have number of nodes more than like 40 or like 30, around that order of magnitude. Like the wave, like for this example star is strongly damped. Sure.
Okay, just a quick question to sort of broaden it out a little bit. So one of the things that's fascinated me about these heartbeat stars is whether or not they can provide us some sense of the sort of final product of star formation, as the initial conditions for, that these objects started. And so I don't have a good sense of how fast it is to run these gyre simulations, but is it possible, properly including dynamical tides to say, okay, what is, given the circularization timescales that we observe, where do we think these binaries started out after at the end of the pre-main sequence, for example, in terms of period and eccentricity distribution?
I see. So like basically this is the question about like how fast does the code like give us a like maybe a tidal circularization rate or
for example, like right, if you have an equilibrium tide and that's it, right? I can take an observed system that's a little bit eccentric today and I can go back in time and tell you where it was. I don't think you can do that with dynamical tides. It's not reversible, right, in the same way.
Yeah, like for our case, like if we like feed in Gyrotype a stellar, like given stellar model, it usually like takes like pretty fast to get a like time scale like for orbital shrinking at a given like, or like if you also give a code, you also need to give a code like some binary elements like period, like eccentricity, so something like that. So like.
So in principle, like population synthesis is possible if your code was given a set of like if the end of star formation gave you this distribution of periods and eccentricities, Gyre can say, does that end state at a gigayear match what we see in the final population? That's
I think
time scale wise possible with real, not just equilibrium tides. But
like for one given model, like that takes maybe 1 minute to get a number. So like if we feed in like 1,000 or so that's
cool.
There's a question.
This is a nice work, actually. My question is about, I have two questions. One is, which I missed probably, what's the ratio of the heartbeat mode frequency to the orbital frequency? And the second question is like, if you decompose the heartbeat mode, does it have a linear or non-linear combination of radial and vertical oscillations? Because it has to be a combination of these two, right? If it's a heartbeat.
Oh, could you please like repeat your first question?
First question is the frequency ratio of heartbeat mode to the orbital frequency.
Could you please like in detail like about that?
I think the question is, what frequency are the heartbeat oscillations at compared to the orbital frequency of the binary?
Oh, like usually that might be integer. I mean, like or like if we see the Fourier like spectrum of the heartbeat system, it usually have several peaks, and some of the peaks might be like integer of the orbital frequency.
I think in the heartbeat it's starting to show that it's about 90.
Like k equals to 90, 91. Yes, that order of magnitude. Yes. Yeah, KY 54, like the two dominant like peak is 90, 91. Yeah.
Okay. Thank you.
Sure.